Hello. Today in this video, I'd like to talk to you about power and power generation. We're going to talk about the relationship between power and electrical energy, and we're going to talk about the electrical companies and how they deliver power to you and how they figure out how much you owe. Now, we've already seen the concepts of electrical energy and power before, but just to remind ourselves, electrical power is related to the rate that electrical energy is used in a circuit. So just like we talked about power before, where power was work or energy divided by time, in the same vein, in electricity, electrical power, is the same as electrical energy or work divided by time. Now we're going to look at this a little bit differently mathematically here when it comes to power and electricity. What we're going to say is that power is related to electrical potential and current. It's V times I. Now, that's one way we could calculate electrical power, but there's actually a lot of ways we could do that because we know that V, our electrical potential, is equal to I times R. So if I plugged in IR for V over here, I could write this a different way. I would get I times R, or I squared. So P is also equal to I squared R. And then finally, if I solved it a different way and plugged in V over R for I would get V squared over R. And so I actually have four different equations to calculate power. V times I squared times R, or V squared divided by R. Now, let's talk about how to calculate electrical energy. Electrical energy is W, and using my equation from above, I know that electrical energy, W, is P times time. And so all I need to do is multiply each of these equations times the time to find my electrical energy. So I'd get V times I times T, also I squared R times T, and then finally V squared T divided by R. Now this is a lot of equations, and just to show you, this is how it'll actually look in your Regents Physics reference table. So there are a lot of equations for this very simple concept, power and electrical energy. And so what you want to do is pick the equation that is most appropriate for the problem that you're given. So let's go ahead and take a look at a few example problems and see which equations we can use in different places. So our first example says a 110 volt toaster draws a current of 6 amps on its highest setting as it converts electrical energy into thermal energy. What is the toaster's maximum power rating? Well, I know that my electrical potential, which is measured in volts, is 110 volts, and my current is 6 amps. I want to find power. Now, since I have volts, or electrical potential, and current, amps, I want to use a power equation that includes all three of those. Well, looking back on my reference table, P is equal to VI. And so I could say that the power here is V times I, plug in my 110 volts, times my current of 6 amps, and I get 660. Well, our unit for power is going to be the same that we've seen before. You've probably heard of light bulbs being measured in watts. That's a measure of electrical power. And so we're going to say our power is 660 watts. Of course, it would also be perfectly fine to say volt amps as your power, but that'd be a little bit weird. So we're going to say 660 watts. For our second example, it says we have a potential drop of 50 volts. So V is 50 volts. It's measured across a 250 ohm resistor. So 250 ohms is our resistance. We now want to know what's the power developed in this resistor. Well, again, we want to pick the appropriate power equation for the variables that we're given. Now here, we don't have V and I, so we're not going to use the same equation. Now we have V and R, and look, V squared over R is also equal to power. And so we're going to say that power is equal to V squared over R. Now plugging in our variables again, we have 50 volts squared divided by 250 ohms. 50 volts squared divided by 250. When I do that in my calculator, I get 10 watts. So what you're going to see is that we want to pick the equation that's most appropriate for the variables that we're given. Unfortunately, there are a lot of equations, and they're written in a weird way, but we don't want to let that fool us as we're solving these problems. Now, finally, for number 3, we have an electric iron operating 120 volts, and it draws 10 amps of current. We want to find the heat energy delivered by the iron in 30 seconds. Well, now we're not dealing with power, we're dealing with electrical energy. That is W. We want to find the amount of energy delivered. Now, I know the voltage is 120 volts. I know my current is 10 amps. And finally, I know my time of 30 seconds. Looking back on my equations, I have an equation for work or energy that's in terms of voltage, current, and time, VIT. So we can say the electrical energy, W, is the potential times the current times the time. So we're going to end up plugging in our numbers, 120 volts times 10 amps times 30 seconds. That should end up in your calculator as 36,000. And remember, our equation, or our unit of energy, is joules. Of course, it would be perfectly fine to say volt, amp, seconds, but let's go ahead and use joules here. Okay, so hopefully you've seen now how to calculate power and electrical energy, but let's kind of have a more fun example. I don't know how many of you guys ever get yelled at home for leaving lights on. That's something that happens in the Baker household all the time, where I leave a light on a little longer than my wife might like me to, and then she's yelling at me to turn it off. Now, I have tried to show her the math a million times, and she doesn't believe me. So I want to show all of you, so hopefully you can help me convince her why it doesn't matter if I leave the lights on a little bit extra. So what we're going to do, let's take a typical light bulb. A typical light bulb, let's say the power of a typical light bulb is like 60 watts. And honestly, that's a little high. These LEDs, these fancy things we have now, they draw even less current, which is nice. So they'll have a less of a wattage. But we're going to take a pretty big case and say, hey, look, we got 60 watts here. Now, let's say that I leave this light bulb on for 20 hours a day. And we're going to do that for an entire month. So 20 hours a day for 30 days. I want to figure out how much it costs me to run that light bulb. Well, to do that, we need to know how much energy that we're actually using. We want to find the amount of energy there. Well, we know that energy is power times time. Our power is 60 watts, and our time is 20 hours for 30 days, which would be a total of 600 hours for our entire month. So 600 hours, which is 60 times 600 is 36,000 watt hours, which you might not think is a useful unit, but that's actually what our power companies, our electrical companies, use to calculate how much we owe them in terms of money. We're going to convert that, though, to a unit you might be more familiar with, hearing from your power bill. 36,000 gets converted to 36 kilowatt hours, a unit you might have heard of before. Now, many of you are probably not paying your electrical bill, but next time you're at home and you know your parents are paying one of the bills, ask them if you can take a look at the electrical bill. You'll notice they charge you in kilowatt hours, and it's kind of interesting. Now, currently in Rochester, things can kind of vary depending on where you live. So we're just going to kind of use an average, but the average from kind of the bills that I've seen at my house are that it costs 13 cents for every kilowatt hour. So we're going to go ahead and multiply my 36 kilowatt hours times 13 cents, or $0.13. Don't even get me started on how to convert those two. I've seen people who do really weird things. So 36 kilowatt hours times 13 cents per kilowatt hour, I end up getting a grand total of $4.68 to run my light bulb. So next time I'm in an argument with my wife about how much I'm leaving the lights on, I'm going to slip her a $5 bill and say that's going to run my light bulb for an entire month, 20 hours a day. You try that at home too, see if it works for you. I can almost guarantee you it won't work for me. Now, there actually is a reason we want to look at this. Hopefully, in the next few days, we're going to be taking a look at how to figure out how much different things in our houses actually use in terms of power and how much they cost us to run per month. And so what you want to know is how to not only find out electrical energy in terms of joules, but also this other unit of kilowatt hours, which is a useful unit for calculating power from the electrical company. That's all I have for today. Thanks for watching, and I'll see you next time.